Hey everyone, this is Dr. Walker. In this video, we're going to go over another example, finding the electric field due to two charges. So it will be similar to the previous example, but we will use unit vector notation and we will make some really cool discoveries. So in this case, we have a charge Q1 that is equal to Q and a charge Q2 that's equal to negative Q. I've labeled them here below. And their distances A and B from the origin, and there's a point P over here at point 0y, and this is the point at which we're trying to find the components of the net electric field. So let's kind of see what's going on. We know that at this point P there's going to be an electric field produced by both charges. Positive charge produces a field away from it, so there will be a field in this direction away from Q1. And then a negative charge produces a field towards it, so there's going to be a field downward in this direction. And we're trying to find the net field. Now, I didn't draw these vectors to scale, but we actually know that the vector E1 is going to be bigger than E2 because charge Q1 is closer to the point than charge Q2 according to this picture. So we are trying to find a net field, which will go somewhere in this direction. And the best way to do that is to find the individual fields, look at the x and y components separately, and add those separately to find the components of the electric field at point P. I have written the expression to find the electric field. So to find E1, it's Coulomb's constant times the charge 1 divided by R1 squared. R1 is the distance from the charge to the point. So R1 is going to be this distance right here. And we can see from this picture that the bottom leg has a length A and the vertical leg here has a length Y. So R1 is going to be given by the Pythagorean theorem. It's going to be the square root of a squared plus y squared. So that's our R1. So we can plug in what we know, KE, and then Q1 is just Q. And then R1 squared is going to get rid of the square root. It's going to be a squared plus y squared. We still need the unit vector R1. So R1 is a unit vector that points away from the charge Q1 towards the point P. To find a unit vector, we can do that on the side over here. So R1 hat is going to equal the vector R1 divided by the magnitude of R1. To find the vector R1, which is the position vector from the charge Q1 to the point P, we know that to find that position vector, which goes to the right and upward, we have to go to the right a distance A and then upward a distance Y. So we can write the vector R1 as A in the I direction plus Y in the J direction. And then the magnitude of R1, we already said, was a squared plus y squared, the square root of that. So we have our unit vector. We can go ahead and plug it in here. We're going to have KEQ, and then in the denominator, since we have a squared plus y squared times the square root of a squared plus y squared, we can write that as a squared plus y squared to the 3/2. Then we're going to multiply all of this by a, the I direction, plus y, the j direction. Let's do the same thing for E2. It's going to be very similar. We're going to have KE, and then Q2 is going to be negative Q. So the Q itself is just a magnitude of the charge. And then we need a distance R2 squared. So R2 is this distance over here on the right from Q2 to the point P. And it will use the Pythagorean theorem. It will be the square root of b squared plus y squared this time, since the leg has a length b instead of a. So when we square that, we will get b squared plus y squared. And we need the unit vector R2. So let's go ahead and find that on the side. R2 unit vector equals R2 divided by its magnitude. So the position vector R2, which goes from Q2 all the way to point P. To get there, we have to go to the left a distance b and then upward a distance y. So we can say negative b in the I direction plus y in the j direction. We're going to divide that by the magnitude, square root of b squared plus y squared. And now we are ready to plug in everything that we know. We're going to have KEQ. I'm going to distribute the negative to this term over here. In the denominator, we're going to have b squared plus y squared to the 3/2. And then in the numerator, since I'm distributing the negative that was here, it's going to be b in the I direction minus y in the j direction. We're almost done. Now we need to find the net field, vector E. And we know that to do that, we have to sum up all the x components separately and then sum up the y components. So let's go ahead and sum up the x components. So from E1, we're going to have KEQ over a squared plus y squared to the 3/2 times a. And then from E2, we're going to have plus KEQ times b over b squared plus y squared to the 3/2. All of this is going to be in the I direction. So this is the x component of E. We can call it EX. And then for the y component, we're going to have KEQ times y over a squared plus y squared to the 3/2. Taking this component over here. And then taking the y component from E2, it's going to be minus KEQ times y over b squared plus y squared to the 3/2. All of this will be in the j direction. So we have found the x and the y components of the electric field by writing it in its component form. In the next part, we're going to simplify this a little bit so that it doesn't look so clunky. In the next part, it says evaluate the field in the special case that Q1 is equal to Q2, that the magnitudes are equal. Now we already knew that because we already wrote Q1 was Q and Q2 was negative Q. But we're going to make the additional simplification that A is equal to B. So that means this time that we can say that Q2 is at a distance A from the origin. That's going to simplify things a lot. So Q2 is not going to be over here. So if we look at how that's going to simplify things, I've written down our answer from part A, and now we can see that we can make all the B's equal to A's. And then we can see that both of these terms are equal. So for E over here, we're going to have 2 times KEQ A over A squared plus Y squared to the 3/2. And that's going to be in the I direction. If we look at the Y components here, if we make the B equal to A, now these terms are identical, but they subtract, so they cancel out. So the net field does not have a component in the Y direction, and this is our answer. This is the electric field at point P when A is equal to B. So what this means is that we're finding the electric field above the midpoint of this electric dipole. I forgot to mention it earlier, but when you have two charges and they have the same magnitude but opposite signs, that means that this is a dipole. That's why this is a special case. This is a special example that we can figure out what happens when you have an electric dipole and you're trying to find the electric field at a certain distance away from it. So let's look at the last part. This last part, I have called it an electric dipole here, and I have written down our answer from part B. And this time, we're trying to find a field when P is a distance y is much, much greater than A. Now, before we do that, I just forgot to mention one thing in the previous example, the previous part, just to show you that when the distances are the same, then when we have one field going this way and one field going this way, that we can see that those y components cancel out and that we do get a net field all in the x direction. I meant to draw that for us. Okay, so now let's take a look at this last part. The point P is now really far away. So what this means when we look at our previous answer is that in the denominator over here, if y is much, much greater than a, then it's going to dominate this expression and effectively cancel out the contribution from a squared. So we're going to get 2keqa divided by y squared to the 3/2, which is y cubed. And this is going to be, once again, in the I direction, in the x direction. So what's really interesting here is that when you're really far away from a dipole, at a certain distance, in this case it's called y, but usually the distance is called r, the dependence is on 1 over y cubed, rather than for a point charge, it's 1 over y squared. So we do see a significant change when we're looking at the field due to a dipole versus a point charge. So that's it for this example. I hope that it was useful.